Okay, the next part then. You might remember in the previous video, we looked at how we can make these equations from a velocity time graph. And there was a question where I said, oh, we don't have to use this, we can use another equation. But actually, we hadn't revealed that yet. So we're going to look at that now. Okay, what we can do is we can think of these as our two initial equations. But if we use them together simultaneously, you can derive lots of different things. So you might think to yourself, well, what would happen if you rearrange this one, for example, so that it was t equals, so you have v minus u, wouldn't you? You'd have v minus u over a equals t. Well, if you did that, then you could plug that result in here. And what you do is you would derive this equation here. So v squared, u squared, these are the same, they have the same meanings as the lesson before, okay? But look, 1, 2, 3, 4. We've got another situation where we can link 4 of the things. So if you know 3 of them, you can find the 4th, okay? For a very hard question, maybe you know 2 of them and you don't know 2, and you have the same somewhere else and you do it simultaneously. That would be a very hard question. But the point is, it follows the same sort of pattern as these equations up here. 4 pieces, normally you get given 3, you find the 4th, okay? What's interesting about this one is it has no t value. So if you were not told the time, but you were told u, v, a, and s, you could use that one there. That would be a good equation to use, okay? You can use them in other ways. So v equals u plus at. Well, what if you just changed the v here? What would happen? You would end up with this one. And this one will look quite different. This is probably the most useful SUVAT equation that there is. I would say you end up using this one about 50% of the time. So S equals ut plus half at squared. You're going to be using that an awful lot, okay? Especially when we talk about projectiles later, like throwing things up and down in the air and so on. So S equals ut plus half at squared. You'll know that one like the back of your hand by the end. So the sooner you get comfortable with that one and make a point of remembering them, it will help you out. Okay, because you do get given these in the formula booklet, but I would really question how much mechanics you had done if you needed to look at that. Okay, you should be doing so many questions that you should know these fluently. Okay, and knowing them means you know what to look for. Finally, there is one more here, which is vt minus half at squared. It says I've never seen an equation that uses this. I have actually seen one before. So this is sort of like, I like to think of these sort of as being a bit like partners. So this is the main one. And this is about like speed at the start, adding on. And this is sort of like at the end, taking away. That's the way that I sort of remember that one there. Definitely less used though. This is the one that's used very, very heavily. Okay, a couple of questions now, and we've got our 5 SUVAT equations. So there are no more, you'll be happy to hear. We're going to use these to solve things. So a particle is moving along a straight line from A to B with constant acceleration 5 meters per second. A equals 5. The velocity is 3 meters per second in the direction AB. The velocity of the particle is 3 meters per second in the direction of AB. That's a little bit vague, that is. It doesn't say initial velocity. I think that might be a typo. I think it should say the initial velocity or the velocity at A. So let's go with that because that's clearly what they mean. So 3 meters per second. So it has a speed and it has a positive acceleration. So this thing will speed up. So when I find v later or something like that, I would expect it to be a bigger number. The velocity is 18 at B. Okay, so that's what we just said. We expect it to speed up. So we expect a bigger number there in the same direction. Find the distance. Well, distance here, if we're traveling in one direction, it's interchangeable with displacement. So S equals question mark. There we go. Okay. V squared equals u squared plus 2s is the way to go here. Why? Because there's no t value. So make things easier for yourself. Use the one that doesn't have the letter you're not interested in. Okay. A particle is moving in a straight horizontal line with constant deceleration 4 meters. So you're probably getting the idea from now what we're going to do. a straight horizontal line. So again, I would do the same sort of thing. Constant deceleration. Deceleration is negative, so -4. At time t equals 0, so time t equals 0, this is the start of the journey. The particle passes through the point O. Okay, well, let's call it O instead, with speed 13 meters per second. Okay, so speed, well, we don't talk about speed, we talk about velocity, so we're going to have to use it as velocity. But it's moving from O, traveling towards point A. So it's sort of just traveling in this line anyway. And it has a positive velocity, positive acceleration. So we don't really need to overcomplicate it. It's just 13. Okay. Travels towards point A, where OA is a distance. When you write two capital letters next to each other like that, that shows you're talking about a line segment. So that's the distance. So OA is 20. So look again, 1, 2, 3. What's going to happen? They're going to say find velocity or find time. That's what's coming up. Let's check. The time when the particle passes through A. Okay, so there we go. We're going to use something with S and U and A and T. So it's our favorite one. It's going to be this one here. Okay. What's really interesting about this formula is you might notice it's a quadratic. So when you use this one, you'll actually get more than one value. And sometimes one of them might be nonsense, or sometimes they might both be important. So here we get t is 5/2, that's 2.5, and t equals 4. So what is going on here? The times when the particle passes through A. Well, the good thing is the question said times, and we have times here. So that's like a little detail that you need to check. Why is this happening? The reason why it's happening, if you imagine, let's call this one O and let's call this one A. The particle is moving here. And at the start, it's traveling at 13 meters per second. So it's going like this, but it has deceleration. So it's slowing down. There we go. We're at A for the first time. And it would keep going. And then it would stop because it's still slowing down. It slows down the whole way. And then, because the acceleration is negative, it's going to start going backwards. So at 2.5, it goes past here for the first time, and then it goes here, and then it starts to turn around, and at 4 seconds, it's on its way back. So this particle is going like this, and then it's slowing down, and then it's starting to go back, and then it will start to speed up. That's what the particle is doing. So look, there's two values there. There's two times that it works. So that's why we sketch. That's why we try and think about things. That's why we hold pens in our hands and do all of this stuff. You need to do that if you're doing mechanics. You need to get a feel for the situation. The value of t when the particle returns to O. So what's going on here? Is that the same situation? Is that something about A when we return to O? No, it's not. It's something like this. The particle moves and it goes to A and then and it goes back. So this is a longer journey. In other words, the times are not going to be the same. We're certainly not going to use those times over here because it's a different distance. And what did we say? We said that if you have a different distance, you're going to have a different time and a different speed. These things are all interconnected to each other. So we need to start from scratch. What we do is we write down our S, our U, our V, our A, our T, and we think carefully. Is there anything that we can reuse from earlier in the question? A particle is moving in a straight horizontal line with constant deceleration -4. It's constant. It never changes, no matter where it is. So A is the same. At time t equals 0, the particle passes through with speed 13. So if there is a longer journey, does that change the speed at the start of the journey? No, it doesn't. So that is still 13. So think about what we said earlier. We said that U and A often get carried over throughout a question. But S and V and T, when one of them changes, the other one will change. So we need one more detail of SVT. Find the value of T. Okay, so that's my question mark. In other words, we need S or V. So what do we know about when the particle returns to the start? we know that its displacement is 0. So that's the 3 bits of information that we put in to find our values of t. T equals 0. Why is that there? That's there because the particle was at 0, was at O at the start. That makes sense. So we must be interested in this one here. This is when it's gone away and then come back. That's that time there, 13/2. Lots of really important ideas there. The U and the A carrying over again, thinking very, very carefully about the situation, drawing it each time, okay? And recognizing that S and V and T are all connected. When one changes, the other ones will change too. So have a go at that question there on the board to test your understanding and see if you can put into practice some of those ideas that we talked about before. You should spend a little bit of time on this question. Pause the video and have a go. Okay, so I'm going to assume that you've paused there. Let's take a look at the answers and we'll talk through. So straight horizontal road, constant deceleration, passes A with speed U. So that sounds like we don't know what the U is. That sounds like a question mark to me. 10 seconds later. So what happens 10 seconds later? It passes through point B with speed 34. So that's like a later speed, a later velocity. And the distance, so look, the time and the velocity and the distance, they're all about the same thing. So they all go together. Well, you have 3 pieces of information. You can find U using one of the SUVAT equations. Okay. What's the time taken to move from A to, not here, but to the midpoint of AB? Well, what's going to change? That's going to change. And if the distance changes, you would expect the speed to be different because it's at a different point in the journey. And if it's half the distance, well, it's not going to take as long, is it? So the time's going to be different. What about U and A? Because you found U before. Well, you know that U is not going to change. The start of the journey is 14. It will still be 14. So you can reuse U equals 14. Is there anything else you could do? Well, you could also use this information for the whole journey to find the acceleration, because the acceleration for the whole journey is the same as the acceleration for the half journey. It's constant. It's the same throughout the whole question. So you would use these here. You would use these to find your A value, which is 2 apparently, so that when you are working on the rest of it, the midpoint of AB, well, that's the midpoint. That's 120, isn't it? So there you go, 1, 2, 3, and we're looking for T. That's how you can solve that one there. So it's a very, very important idea, recognizing that A is the same throughout because of constant acceleration, and the U, no matter whether you make your journey shorter or longer, that the U should remain the same number also. Okay, and that brings us up to 9D in the book.